Hello everyone, this is another video on quantum mechanics where we'll be discussing about uh, identical particles, okay, which is again another important concept for GATE exam. Identical particles. In the previous sessions, we discussed about spin angular momentum, okay, and we also did some numericals. So here we'll be discussing about identical particles, also be solving numericals. All right. So we know there'll be two kind of particles, that is your bosons and fermions. Okay, even this is even integral spin. That means it will be like 1 2 3 etc like that. This is a odd integral spin. Okay. Half odd integral or odd integral spin, that means it should be 1 by 2, 3 by 2, 5 by 2, right? Yeah. So uh, so the wave functions of these things will be what? So the wave function, if we talk about wave function, if we talk about the wave function, so first one is a symmetric wave function. First one is a symmetric wave function, that is, it remains unchanged, remains unchanged under the exchange of particles. Under the exchange of particles. Okay, so psi symmetric is equal to 1 by root 2 psi 1 2 plus psi 2 1. Okay, now another is antisymmetric or asymmetric. Antisymmetric, that will be wave function remains what, it will change, it changes sign, wave functions changes sign under the exchange of particles. Under the exchange of particles. Okay, so psi antisymmetric will be psi antisymmetric will be 1 by root 2 psi 1 2 minus psi 2 1. Okay, so the total wave, we know what is total wave function. So total wave function is what? Psi total is equal to, it's written as psi spin part wave function into psi space. Okay, and this psi space is a what? Symmetric or antisymmetric. Okay. Symmetric is who has symmetric wave function. Bosons have symmetric wave function, and fermions have antisymmetric wave function. Okay, yeah. So next is mm, total number of wave functions is total number of wave functions is equal to n factorial. Okay, n factorial. Okay. So next is that degeneracy rises due to exchange of particles. So degeneracy formula is degeneracy is n factorial. Okay, degeneracy is n factorial. Now, mm, now is given a particle exchange operators. particle exchange operators. First is eigenvalue. What are the eigenvalues? Eigenvalues are plus or minus 1. Next is a Hermitian operator. Hermitian operator Shapra is what? How is it written? P12 like dagger is equal to P12. Dagger means complex conjugate. Okay, or this. Then involuntary operator. Involuntary operator what is it? If P12 square is equal to I, that is an involuntary operator. Okay, I for unit matrix actually, but you remember this way. Involuntary means I square is equal to I. Okay. Next is if potential is symmetric. If potential is symmetric under exchange. Potential is symmetric under exchange of particles. Okay. Then the commutator of that operator with Hamiltonian will be 0. H P12 is 0. Okay. All right. Mm, Next is another important point is quantum identical particles. Quantum identical particles are always indistinguishable. Can be, sorry. No, leave it. Leave this point. Next point is spin states. Spin states. For n particles, total number of spin states is equal to 2s plus 1 to the power n. Okay. For n is equal to, for example, n is equal to 2, s is equal to half. So what is the total number of spin states? Number of spin states equal to 2 into half plus 1 whole square. That is 1 plus 1 that is 4. Alright. So SMS we can write 0 0. This is called a singlet state. Okay. Here s is 0. Otherwise, if s is 1, we can write it as 1 1 1 0 1 minus 1. Okay. Yeah. So number of states is equal to 2s plus 1 whole square. It's different for different. For symmetric is s plus 1 1 to s plus 2 2s plus 1. This is for symmetric, and for anti-symmetric it is s 1 into 2s plus 1 anti-symmetric. Alright. Yeah. Okay. Next is what? Next is, see, this is a psi total. Okay. can be psi total for symmetric. If I write symmetric, it will be psi space into psi spin we know. So both can be symmetric. Okay. But if I write for antisymmetric, psi space into psi spin, so both should be what? Antisymmetric. Okay. Now if I write psi total for antisymmetric, okay, that asymmetric or antisymmetric, same thing. So psi space into psi spin. This should be symmetric, this should be antisymmetric, or the vice versa, isn't it? Or the vice versa. Alright? Yeah. So now, so these are the stuff. Now we'll do some numericals. Okay. Question number, I think in the previous class it was 42. So this will be question number 43. So which of the following is not a boson? Okay. Boson means what? Boson means what? First of all, how to define boson? Okay. If we have the even number of proton and neutron, even number of proton and neutron. Why? Because proton they have spin half, isn't it? Spin is half. So if I have even number for four protons, so spin will be 4/2. That is two. Two is your boson. Spin is two. That is a boson, isn't it? For example, I have three protons. If I have three protons, then what will happen? 3/2. So this is a fermion, isn't it? This is a fermion, right? Yeah. So, um, so here if we yeah. So see for helium 2 4 otherwise like total number of protons and neutrons helium 2 4 number of protons is 2 number of neutrons is 2. So what 2 into half plus 2 into half, right? Spin is 2, so spin is even. So this is your boson, isn't it? Even into. Now hydrogen 2, 1 proton 1 neutron, that means 2 overall. So that will be even also. But helium 2 3, if you see, two protons, one neutron. So this is like 3. So 3 into 1/2, that is 3/2. So 3/2 is what? Fermions. This is not a boson. Okay, photon. Photon is a boson. Okay, photon is a boson. Is it clear? Yeah. Okay, next question. Question number 44. So two fermions of spin 3/2. Two fermions are there. Spin is 3/2. So find degeneracy of space part. So if you see the formula, degeneracy of space part. What is this formula? Where is it? See, degeneracy of space part is asked in this question. Okay. See, two fermions are there. Both have spin. It's 3/2, 3/2. Right? Both have spin 3/2, 3. So S is what? S1 plus S2 to S1 minus S2. So 3, 2, 1, 0. Okay. So parity we know. Parity is what? Minus 1 is plus 1. Okay. So if it is positive, that is a space part. If it is negative, this is called a spin part. Okay. So how can we get it positive? If ace is odd, I will get this as whole thing as even and this will be positive. So 3 1. Negative. How will I get the spin part? If it is even, ace is even, 2 0. Got it? 2 0. Yeah. Okay. So degeneracy. How will I write degeneracy now? Degeneracy I will write here. So if s is equal to 1 and s is equal to 3, degeneracy space part. Okay, space part means I will learn only for 3 and 1, right? S is equal to 1, S is equal to 3. So degeneracy was 2s plus 1. This is your what? 2 into 1 plus 1 is 3. It's 2 into 3 plus 1, that is 7. So total degeneracy is 10. For example, you want to ask degeneracy of spin part, spin, space, spin. S is equal to 2, S is equal to 0. Okay, so yeah, I would have done the same way, right? Yeah. Okay. So answer is 10, right? Yeah. Next question. Let's go to the next question. Question number 45. Question number 45. A two-dimensional square rigid box of side L contains six non-interacting electrons. So six non-interacting electrons are there. At this much, the mass of electron is m. The ground state energy of the system of electrons in units of system. So two-dimensional square rigid box, 2D box. What is the energy of 2D box? N square, nx square plus ny square, because length is same, l square, nx square plus ny square, pi square h cut square by 2ms square. Alright. So six electrons are there. We have six electrons. So if I arrange the six electrons, it will be like this, isn't it? It will be like this, right? Ground state energy of the system is asked. Ground state energy. So see, this is it. This is the arrangement. So this one will be 2 into, this is what? 1 plus 1 pi square h cut square by 2 m square. That is y 1 plus 1. Nx is 1, ny is 1. This is 1. Okay. 1 1. 2 1 and 1 2. Degeneracy is 2. Okay. So 2 into 2 pi square h cut square by 2 m square. Then this is a 4 into what? 4 plus 1, 5. Okay. 4 plus 1 pi square h cut square by 2 m square. That is 4 into, so plus 4 into 5 pi square h cut square by 2 m square. If I calculate it, it will be, this is how much? 4 by 2, this is 20 by 2. 24 by 2 pi square h cut square by m square. M square. So answer is what? 24. Isn't that right? Isn't it? Because the we cannot write it as 2 2 now, because there is a degeneracy 2 1 1 2 have the same energy, that is, isn't it? So we have to take the degenerate part also. We cannot just skip to 2 2. Alright? Yeah, that's the answer. 24 is the answer. Next question, question number, what was the previous question? Question number 46. Question number 46. Consider a system of 8 non-interacting identical particles of spin 3 by 2 in 1D box of length L. The minimum excitation energy of the system is. Consider a system of 8 non-interacting identical quantum particles of spin 3 by 2 in a 1D box of length L. Okay. 8. Now there are 8 electrons. Sorry, no, 8 particles of spin 3 by 2. 1D box of length L. So energy of 1D box is how much? N square pi square h cut square by 2 ml square. So 8 particles, spin is 3 by 2. So how did you, in the previous question, if you see, how did I decide that there will be 2 electrons here? Because electron spin is half. So multiplicity will be 2s plus 1. Multiplicity means like number of electrons in one state. So 2 into half plus 1, that will be 2. So maximum 2 electrons can be fitted in one state. So here what? The spin is 3 by 2. So S is 3 by 2. So how many like particles in one state? 2 into 3 by 2 plus 1. That is 4. So 4 particles can be fitted in one state. Okay, 4 particles can be fitted in one state. So one, two, three, four. Okay, one, two, three, four. That's it, eight. But the question is what the minimum excitation energy of the system. This is what. This is the minimum. This is the ground state. This is what. This is the ground state. What is the excitation state? If I put take one particle to the above state, that will be your excited state. So let's do it. Let's take the other particle to the excited state. One, two, three, four. One, two, three. Now one. Okay. First of all, let's calculate the ground state. Ground state will be how much? This is 4, 4. Okay. This is your what? What is the n? N is equal to 1. N is equal to 2. There is no degeneracy because it's only 1D box. So 4 into pi square h cut square by 2 ml square plus 4 into what? What is the next state? 4 pi square h cut square by 2 ml square. So the answer is 4 plus 4, 4 plus 16. So 20 pi square h cut square by 2 ml square. Alright. Now here excitation happened. So now n is equal to 1, n is equal to 2, n is equal to 3. So again, if I see this is 4 into pi square h cut square by 2 ml square plus 3 into 4 pi square h cut square by 2 ml square plus um, uh, what? This is 1 into only one particle 9 pi square h cut square by 2 ml square. So this will be what? 4 plus 12 plus 9 divided by 2 ml square. That is pi square h cut square. 4 plus 16 or 25. 25 pi square h cut square by 2 ml square. But the thing is, question is what? Minimum excitation energy of a system. This is actually you are asked in terms of ground state, right? So ground state is what? 20 pi square h cut square by 2 ml square. Okay, I can write this one as 20 E1. So this one I can write it as 25. Okay. Anyway, no. This one is your E1 now. This one is your E1. Round straight. 20 pi square square. So what will I do now? See, I will multiply 20, divide 20 pi square h square by 2 ml square. So this I can write 25 by 20 into 20 pi square h square by 2 ml square. This is my ground state. So 25 by 20 E1. Isn't it? Right? Isn't that correct? Yeah. Yeah. Otherwise, uh, what is asked in the question? The minimum excitation energy of this. Oh, okay. Excitation energy. Okay, I get it. Excitation energy means how much energy is required for this particle to go from here to here. That will be simple. E excitation will be what was this state? 25 E1. Right, 25 E1. If I write it 25 E1 minus 20 E1. That was the previous one, the ground state. 20 E1. If I write it. Okay. So it will be how much? 5 E1. That is the answer. Okay. Let's move to the next question. Consider a system of two non-interacting identical fermions. Each of us aim in a infinite squirrel potential width A. Take the potential cell well to be zero and ignore spin. Composite wave function for the system with total energy. Okay, so this is a fermion. Total energy is 5 pi square h square by 2 ma square. Two identical particles in an infinite square wave potential of width A. Okay, so how to do it? So we know that for fermions, wave function is antisymmetric. Okay, so if we because a total wave function is what psi space into psi spin. Here it is saying that to ignore spin. So if you ignore spin, that means what is left? Psi total is equal to psi space. Psi total is antisymmetric, so psi space will be also antisymmetric. Okay, psi space is antisymmetric, right? So first of all, the energy is n square nx square, two particles, na, ny square pi square square by 2 ms square. Okay, so 5, this is your 5 actually, 2 ms square. So 5 is equal to what? Nx square plus ny square. So nx is equal to 2, ny is equal to 1, or nx is equal to 1, ny is equal to 2, like that, right? So this is antisymmetric. Can I write it like psi? I can write it like what? How can I write it? Psi 1, 2, 1, like 1 by root 2. Okay, psi 1, isn't it? Right. This is the way to write it. Otherwise, I can write it this way: 1 by root 2 is normalization factor. Like, what? Root 2 by a sine pi x1 by a into root 2 by a sine 2 pi x1 by a, minus will be there, root 2 by a sine 2 pi x, sorry, this will be x2, 2 pi x1 by a root 2 by a sine pi x2 by a. Okay, if I simplify it a bit more, that would be your 2 by a sine pi x1 by a sine 2 pi x2 by a minus 2 by a sine 2 pi x1 by a sine pi to x by, right? This is the answer. Okay, this is a what? A function. Alright, is it clear? Okay, next question. The ground state energy of this was what number question? 44, 5, 6, 7. This is 47. 48. Ground state energy of five identical spin-half particles which are subjected to a one-dimensional single harmonic oscillator. Ground state energy of five identical spin-half particles which are subjected to a one-dimensional simple harmonic oscillator. One-dimensional means En is equal to n plus half h squared omega. Right. Five identical spin-up. Spin-up means how many particles can be in one state? Two. Okay. So 2 here, 2 here, 1. This is your what? H squared omega by 2. 2 into h squared omega by 2, 2 into 3 by 3 h squared omega by 2, 1 into 5 h squared omega by 2. So if I add everything, it will be what? 2 plus 6 plus 5 h squared omega by 2. That is 13 h squared omega by 2. That is the answer. Okay, answer is 13. Question number 49. Two electrons are confined in a one-dimensional box of length L. One electron states given by psi nx is equal to root over of 2 by L sine n pi x by L. What would be the ground state wave function psi x1 x2 if both electrons are arranged to have the same spin state? Two electrons are confined in a one-dimensional box of length L. One-dimensional box. The one electron state is given by this. What would be the ground state wave function if both electrons are arranged to have the same spin state? So same spin state means both will be up or both will be down. So when electrons we arrange normally what? If these are some states like this, up down, right? But if they're in the same state, can we do it? Can we do it? No, we can't do it because this will violate Pauli exclusion principle. That is, no two fermions can be in the same state, like, right? They can be like this, but they cannot be like this, both of them. So what will I do? Two electrons. So what will I do? I will just put them separately. That's it. As simple as that. Okay. And what will be the then what will be the ground state energy? constant wave function. Sorry, constant wave function for it. As this is a fermion, this is electrons are fermions. This is n is equal to 1, this is n is equal to 2. So I can write it as psi x1 x2 is equal to 2 by L, 2 by L sine pi x1 by A, pi x1 by A or L sine 2 pi x2 by L minus sine 2 pi x1 by L into sine pi x2 by L. Alright? Yeah? Okay. So this is a minus sign is for what? It's for antisymmetric because these are fermions. Alright? That's it. Okay, next question. Read the question. Which what number this question was? 49. So yeah, this is the half century. 50. This is 50. Try read the question first. Read the question. Find the number of symmetric and antisymmetric states for the system consisting of two identical particles. Find the number of symmetric and antisymmetric states for a system consisting of two identical particles. Number of symmetric and antisymmetric. If you remember that table that one we did. First of all, total number of states given at least is what? 2s plus 1 to the power n. Okay. So 2 into spin half plus 1 particles are 2. So 4. Okay. Now number of symmetric states will be equal to s plus 1 to s plus 1, right? So that will be half plus 1 2 into half plus 1, 3 by 2 into 2, that is 3. Okay. Number of antisymmetric states, that will be s1 into 2s plus 1. This formulas you have to remember. Okay. This is 1. Okay. So 3 plus 1 is 4. Total numbers is 4. Alright. So this is the question number 50. So a lot of questions we did from this particle, from this part, that is identical particles. Okay, this is not enough. We have to do more questions, like which we will do in upcoming sessions. You can see we have already done 50 questions or 50 questions. At least one question, one type of question will come in exam or not. So at least 2 marks we are getting from this. At least like whatever we have done so far. Okay, so keep tuned with me. I'll be providing more numerical sessions. Okay, yeah. Thank you very much for attending.